Herholt didn't have the records to prove that he did this, and Hall had these meticulous records. And so for a long time, you know, we in America said, oh, it's the Hall process, Hall did it. And we knew full well that Herholt should get some of the credit, and so a few years ago they began to call it the Herholt-Hall process. And that's probably what we should do. But we always have this problem of people trying to claim who did what first and who got there, because it brings a lot of honor and sometimes a lot of money. It certainly did to the Aluminum Company of America. All right, we have looked now at the processing of, a little bit of the processing of steel and iron. We looked at the processing of copper, and we looked at the processing of aluminum, but we cannot melt everything that we want to refine. So let's take a brief look at trying to refine something like tungsten. Tungsten is a material that melts at 6,100 degrees Fahrenheit, approximately. It's the highest melting point material we have. And we're not going to run a process and wind up with molten tungsten very easily. We don't have anything to hold it in. So how in the world are they going to do this? They do the same thing that they do in the Hall process. They find the ore and they refine the ore to bring it to a pure molybdenum oxide state. We may be finding molybdenum disulfide. We have a lot of that in this country, by the way. But this particular ore, this lubricating, this greasy feeling material, this good lubricant that we have, we can convert to an oxide if it's molybdenum. In the case of tungsten, we take it in whatever form we can get. In both cases, we convert it to an oxide, a pure oxide. Now, if we know it's pure oxide, and we know it will react with carbon or hydrogen to take the oxygen away in the form of carbon dioxide or water, all we have to do is to very carefully put the exact right amount of carbon with it. So we will take the powdered, let me use, for instance, molybdenum. That's a nicer one to describe. Take the molybdenum oxide powder, mix it with just the right amount of carbon, heat it up in a vacuum, and what we're going to expect is we're going to get carbon dioxide, which we're going to pump off in the vacuum, and we're going to have left behind powdered molybdenum. And we don't have to get it molten to do this. We have to get it hot, perhaps, but not molten. But now we have all of this powdered metal. And how are we going to get it to be one piece? Well, we put it in a big press, and we squeeze it together, and it's like playing sandbox. You know, you squeeze it. If you squeeze it hard enough, you get the little particles to plastically to flow, to interlock, to stay together. It's a green compress. You break it up, drop it on the floor, it'll break all apart. But we can put it between, say, two electrodes and pass a high current density through it in a vacuum or in an atmosphere now, so there's no oxygen around, nothing that will react with it around. And we don't get it up to its melting point, but we get it very, very hot. And we find that the material will sinter together. It will, each little particle will join to the next little particle, and then we wind up with a bar of material which may be partially porous, but it has a lot of strength because it has a lot of bond points, and we can coin that material. We can squeeze it to mash out all those little pores and put it back in the system and heat it up again, and we have now a piece of tungsten, the most ductile material in the world, and we can start wire drawing it and pull it down to these very, very fine, tiny filaments that we make all sorts of incandescent electric light bulbs and the like. So it's a powder process of producing or refining the material, and we do this with many materials. Actually, once we get the molybdenum in its refined state, we use an awful lot of it today because it is a high temperature refractory material, but it has a very peculiar property. If I were to give you a block of molybdenum, let's say an inch by an inch by an inch, and said, heat this thing up for me, I'm going to give you till tomorrow morning. Make sure when I come in tomorrow morning, I want this thing at 1,500 degrees Fahrenheit. If you put it in the furnace, just open the door of the furnace and put it in and turn it up to 1,500 degrees, and you came in the next morning, you open the door, the molybdenum wouldn't be there. And it has a melting point of about 5,400 degrees. So what happened to it? But your laboratory would be loaded with beautiful yellow crystals. And what happens is that the aluminum forms an oxide. But aluminum oxide evaporates, sublimes at 1,200 degrees, 12 to 1,300 degrees Fahrenheit. So you sit it in an oxidizing furnace, it makes an oxide, but the oxide isn't stable, and so it evaporates And so you have to do all of the work with it in a controlled atmosphere. But once you get it in a solid state, you can work in controlled atmospheres, and you can rework or remelt little bars of it in copper liners that we keep water cooled so the copper never gets above its melting point, and yet we retain the molybdenum molten inside of it, and we arc melt the material, and we can build up great big ingots of it, and we can make big slabs, and we can make plates, rods, anything we wanted of it. But we started way back there with a little bit of powder. I want to look now just once at the iron process again, or the steel process. And you remember that when we looked at this once before, we came to the casting operation, which was at this end of the total flow chart. We cast it into steel ingots. Now, the thing that's expensive, has been expensive down through the centuries, is to make a hot fire. Anytime you have to melt something, anytime you have to make a fire, well, you all know this. If you heat your houses, you know this. It costs money, right, to burn anything up. If we are going to the trouble of melting a material and then solidifying it and cooling it off and then have to reheat it so we can further fabricate it, we're losing a lot of money. We're losing a lot of energy. We're also polluting the atmosphere thermally. And so it is advantageous to omit this step of casting into an ingot form. The big technology today in the steel industry that has put us way ahead of where we were even just 6 years ago is to learn how to cast these steels, a steel that's now prescribed steel. You make up the spec you want, and you continuously cast it into essentially, well, it's what's called a 4-hearth or a ton dish, or a container, just a big bucket that has a hole in the bottom. The hole that's in the bottom is going to be specially designed so we can water cool the outside. If you poured the material in there, it would run right straight through. So what you do is you stick a piece of steel approximately the same size up from the bottom, so if you pour the steel from the top, it can't run through, all right? But now it starts to solidify because we're dumping water on the outside of this jacket. We're taking the thermal energy away. And it takes away the latent heat of fusion. As it takes the latent heat of fusion away, and we solidify it, we begin to withdraw the steel bar that's in the bottom. And as we pull it away, the molten material feeds down into this water-cooled chamber and solidifies. Just a thin shell on the outside. Actually, when it emanates from that die, there's more water to be sprayed on it to cool it on down, to completely solidify it. And you notice in this process, we'd never get a pipe, because the material is solidified from the side, but we're always feeding it from the top, right? And we make continuous castings of steel, and we take these out in what we now call strand mills. And that saves so much energy and so much time in the production of a part. And we don't have scabs, we don't have seams, and we don't have pipes, we don't have those kinds of defects. And we can develop other kinds of defects in the material, but it gives us this particular advantage of a rapid production. Just visualize this, and you'll see that if we did that vertically, the material is going to come out vertically, and we want to put it in a rolling mill, I want to do anything else with it, we're going to have a little bit of a problem. Because we may cast an ingot, we may cast a slab, let's say, that's 10 inches thick and say 35, 30, 40 inches wide, may be continuously cast coming down. It's incandescent. It's way up in temperature, 1,800 degrees or 2,000 degrees Fahrenheit. We see it emanating at that temperature. So we have a choice. Either we can turn it around sideways, which we do, and use a flying saw to cut it off as it goes by into slabs that can then be fed into a rolling mill down the line. Or we can design a strand mill that actually casts horizontally. And we have such slab mills today, such strand mills today in this country. We still have a problem, and that is, if we're in an antiquated mill like some of our steel mills are today, you don't have them capable now, this hot material, of immediately feeding it into a rolling mill line, because you don't have the space to build all of that and keep it in line, in tandem. And so you then have a slab, you have to load on a car, take somewhere else, but it still has a lot of sensible heat in it, so you can charge it back in the slab heating furnace, heat it up, and put it through the rolling mills again. So we can consolidate these materials, refine them and consolidate them, and it doesn't make any difference what we got out there, you know, whether it's titanium, magnesium, whether we're using seawater as an ore, or what it is. We have ways of refining them, always, if you look at it the way I've described it to you now, doing the same sorts of things with every one of them, either making nickel or extremely pure and reducing it and then consolidating it, or having an operation that reduces the oxide and takes it away and leaves the elemental molten material behind.
The Hall process made economical production of aluminum possible. Calcining uses cryolite to dissolve aluminum oxide, so an electrolytic treatment can plate out aluminum, which falls to the bottom of the electrolytic cell and is cast. Tungsten is refined by mixing its pure oxide with just enough carbon to produce the metal plus carbon dioxide. Continuous casting is so popular in steel making today because it reduces or eliminates the energy required to reheat the casting after it cools. It also reduces or eliminates many casting defects.
Well, that leaves us now with solid metal and capability of producing all sorts of shapes, but we got to get these things into shape. And we got to couple the shaping operation up now with the property. We started looking at the properties, then we looked at the manufacturing process that's going to change the chemistry. Now we got the chemistry we want, and we know what we're trying to produce up there. Now we're going to have to look at how we're going to get this into usable form. And we get it into usable form now by a lot of operations. But tomorrow when you come back, I think I will show you how to do perhaps continuous casting right here so you can see what it's all about and grab it in your hand. Thank you very much.